Hello everyone, this is an audio lecture for visually impaired students, and in this lecture we are going to discuss about F-block elements. F-block elements are also known as inner transition elements. F-block consists of two series, lanthanoids and actinoids. Lanthanoid series start from lanthanum and actinoid series start from actinum. General electronic configuration is N-2 F1 to 14, N-1 D0 to 1 and Ns2. For F series lanthanoids, these elements are called rare earth. Many of elements are not particularly rare, so this name is not appropriate for the whole series. Promethium is a radioactive element. 5F series actinoids. The members of actinoids are radioactive and majority of them are not found in nature. Elements from atomic number 93 onwards are called transuranic elements and discovered by synthetic methods. Lanthanoids, 4F block elements, general characteristics, electronic configuration. General electronic configuration of lanthanoids is 4F1 to 14, 5D0 to 1, 6S2. Lanthanoids have outer three shells incomplete. They have electronic configuration with 6S2 common but with variable occupancy of 4F level. The energies of 5D and 4F orbiter are also nearly similar, and thus their filling shows certain irregularities. It is energetically favorable to move the single electron on 5D into the 4F level in most of the elements, but not in case of Ce, Gd and Lu. In Gd and Lu, besides 5D, the 4F orbitals are half filled or fully filled. Give extra stability. EU and YB also shows extra stability of half-filled and fully filled F orbitals. This is the series of lanthanoids. Atomic and ionic radii. In lanthanoid series with increasing atomic number, there is a progressive decrease in the atomic radii as well as ionic radii of trivalent ions from La3 positive to Lu3 positive. This is due to lanthanoid contraction. Now, what is lanthanoid contraction? The atomic and ionic radii of trivalent ions decreases regularly due to increase in atomic number from Ce to Lu. This continuous decrease in size of atoms and ions is known as lanthanoid contraction. Due to decrease in the size of lanthanoid ions from Ce3 positive to Le3 positive, the covalent character of MOH bond increases and hence the basic strength decreases. The CeOH thrice is the most basic while LuOH thrice is less basic in nature. Effect of lanthanoid contraction. Size of 4D and 5D series is almost same. Ionization energy of 5D series is more than 3D and ionization of 3D series is greater than 4D series. Oxidation state. The lanthanoids contains 2s electrons in the outermost shell. They are therefore expected to exhibit a characteristic oxidation state of +2, but the +3 oxidation is common in lanthanoids. All the lanthanoids have +3 oxidation state and only cerium, Pr and Tb exhibit higher oxidation state, that is +4. Oxidation state +2 and +4 occur specifically when they lead to a inert gas configuration, a half-filled f orbital, a compound filled f orbital, means completely filled f orbital. Lower oxidation state act as reducing agent and higher oxidation state acts as oxidizing agent. Example, Ce4 positive and Tb4 positive. Lanthanoid shows limited number of oxidation states as the energy gap between 5D and 4F subshell is significant. Magnetic properties. In lanthanoid series, the number of unpaired electrons is tripositive. Lanthanide ion regularly increases from La to Gd 0 to 7 and the continuously decreases up to Lu, that is 7 to 0. So La and Lu ions are diamagnetic and all other tripositive lanthanoids are paramagnetic in nature. Other properties. The lanthanoid ions have unpaired electrons in 4f orbitals, thus these ions absorb visible region of light and undergo F transition and hence exhibit color. The color exhibited depends on the number of unpaired electrons in the 4f orbitals. The ion often with 4f0 configuration have similar color to those ions have 4f14 configuration. All the lanthanoids are silvery white soft metals and tarnish rapidly. Hardness increases with increase in atomic number, Sm being still hard. It is difficult to separate lanthanoids in pure state. These are good conductor of electricity. Alloys of lanthanoids with Fe are called mish metals. Ionization energies. Lanthanoids have fairly low ionization energy comparable to alkaline earth metals. Electropositive character high due to low ionization potential. Complex formation do not have much tendency to form complexes due to low charge density because of their large size. Lu3 positive is smallest in size can only form complexes. Now we will discuss about effect of lanthanoid contraction. Effect on post-lanthanoid. In 5D period, the elements after hafnium including in also are tremendous post-lanthanoids. Atomic size. In general, on moving down the group, the size of atoms increases, but due to lanthanoid contraction, atomic size of HF is almost similar to ZR. Also, ionic size of HF for positive is almost similar to ZR for positive. Size of 4D series is nearly same to that of 5D series. Size of PD is almost similar to PT and size of AG is nearly equal to AU. Properties of 4D and 5D series are similar. Due to this reason, they exist in nature in combined form and difficulty arises in their separation. Within lanthanoid series, properties of elements are similar, so they are difficult to separate as they also form in combined form. Uses of lanthanoids mish metals. 95% of Ce plus 5% Fe. It is a alloy. Cork glass CEO2. In ordinary glasses, SiO2 is present. Cork glass prevent UV light. Lanthanoid oxides Ln2O3. It is used in TV screens and used as catalyst in petroleum cracking. Actinoids 5f block elements, the elements in which the last electron enters in 5f orbital of n-2 main are known as actinoids. The man-made 11 elements Np93 to Lr103 are placed after uranium in the periodic table and are collectively called transuranic elements. TH, Pa and U. First three actinoids are natural elements. General characteristics. Electronic configuration. General configuration of actinoids may be given as 5F1 to 14, 60 to 1, 7s2. The list of actinoids are given below. Now we will discuss about the oxidation states of actinoids. The actinoid shows in general +3 oxidation state. Actinoids show a variety of oxidation state. It is because of a small energy difference between 5F, 6D and 7S subshells. The element in the first half of the series frequently exhibit higher oxidation states. For example, the maximum oxidation state increases from +4 in TH to +5, +6 and +7 respectively in Pa, U and Np, but decreases in succeeding elements. Now we will discuss about atomic size. In actinoids series, size of atom or ions gradually decreases. It is considered as actinoids contraction similar to lanthanoid contraction. Due to poor shielding by 5F electrons, the contraction becomes greater, varies from element to element in the series. General characteristics and comparison with lanthanoids. Instead of having same color, silver, all actinoid metal display the variety of structures. This variety is due to irregularities in metallic radii, which are far greater than in lanthanoids. The actinoids are highly reactive metals. The magnetic properties of the actinoids are more complex than those of lanthanoids. Actinoids compounds or their ions are colored most probably due to FF transition. Actinide contraction is greater than lanthanoid contraction due to poor shielding by 5F electrons as actinoids than that of 4F electrons in lanthanoids. Differences between lanthanoids and actinoids. In addition to +3 oxidation state, lanthanoids exhibit +2 and +4 oxidation states only, whereas in actinoids, in addition to +3 oxidation state, they show +4, +5, +6 and +7 oxidation states. Most of the ions of lanthanoids are colorless, whereas actinoids ions are colored. Lanthanoids do not form complexes easily, whereas actinoids have much greater tendency to form complexes. Lanthanoids do not form oxocations, whereas actinoids form oxocations such as UO2 2 positive, PuO2 2 positive. Lanthanoid compounds are less basic, whereas compound of actinoids are more basic. Except promethium, lanthanoids are non-radioactive, whereas all the actinoids are radioactive in nature. The magnetic property can be easily explained in lanthanoid, whereas the magnetic properties cannot be explained in actinoids. Now we will discuss about the chapter summary. The transition elements are defined on the basis of their incompletely filled d orbitals, since Zn, Cd, Hg elements have d10 configuration and are not considered as transition elements, but they are d block elements. The D block, consisting of group 3 to group 12, occupies the large middle section of the periodic table. In these elements, the inner d orbitals are successively filled. F block elements are placed outside at the bottom of the periodic table. 4F and 5F orbitals are progressively filled for the elements of this block. Metallic nature and physical state. All the transition metals have metallic properties. They have tensile strength, ductile, malleable, high thermal conductivity, high electrical conductivity, metallic luster, high melting point and boiling point. All d block elements are solid at room temperature. Exceptionally, mercury is liquid. Chromium and copper have high ionization enthalpy than their neighbor elements. Transition elements tend to be unreactive with increasing atomic number in the series. The atomic radii do not change very much in a transition series with an increase in atomic number. Generally, middle members of transition series have higher oxidation states, unlike Cr3 positive, Mn2 positive, F3 positive, Fe3 positive, and the subsequent other M2 positive ions of the 3D series of elements. The 4D and 5D series metal generally do not form stable cationic species. The transition elements will vary widely in their chemical behavior. In first series, all the elements are relatively reactive except copper. All of them can be dissolved in mineral acids as they are sufficiently electropositive in nature. The first transition series metal oxides are generally formed from the reaction of metal with oxygen at high temperatures. Potassium permanganate and potassium dichromate are common examples. The two series of inner transition elements, lanthanoids and actinoids, constitute the F block of the periodic table. After filling the inner orbitals for F, there is a gradual decrease in the atomic as well as ionic size of these metals along the series, that is lanthanoid contraction. La3 positive and Lu3 positive do not show any color in solution. Lanthanoids form primarily plus 3 ions while the actinoids usually have greater oxidation state in their compounds, plus 4 or even plus 6 being typical. The actinoids exhibit a large number of oxidation states than the corresponding member in the lanthanoid series. The chemistry of actinoids is more complex in view of their ability to exist in different oxidation states. Furthermore, many of the actinoid elements are radioactive, which make the study of these elements rather difficult. LeOH thrice is more basic than LuOH thrice. Ce4 positive is a good oxidizing agent in aqueous solution.